record to be started. Okay, it started already. So, okay, now we go to the second part of chapter 3. Okay, before this, we actually learn about the introduction and definition of Fourier transform. Okay, now we're going to go part 2 of the chapter 3. So, if you notice some tutorial last time, may use part 2 chapter 3. I mean the in-class exercise. Okay, so we go for these properties of Fourier transforms. Okay, we have A until G here. Okay, we have linearity, superposition, time shifting, time scaling, duality, frequency shift, and modulations, convolution, and differentiation. Say frequency shift is actually when we, for example, we want to modulate signal, information signal. Normally, information signal, for example, it is low in frequency, so it cannot travel longer distance. Okay, so we modulate them with a carrier wave. Okay, with a modulate, we introduce carrier wave, so they able to travel to the further distances. Okay, larger distance. So, for example, of this application is radio. Okay, radio. For example, if you want to listen to Zayan FM or Hot FM, AR FM, whatsoever. So this is actually the modulated signal. For example, if you listen, if they say 32.3 megahertz signal. So it is actually the modulated signal. Your information signal much lower. Otherwise, because if you are using voice, for example, I'm from this school, I'm going to shout, someone from UTMM campus cannot hear. Okay, that's why we need to modulate the signals. Okay, so this you will learn then during your principle of communications. Principle of communication, the later subject after signal and system, I presume. Okay. So, okay, linearity and superposition. I think this one is quite straightforward. Okay, you guys have learned this indirectly, or because sometimes I taught in class. Okay, so linearity is actually when we introduce similar where there is changes in the input, there will be similar changes in the output. Okay, and superposition is just like a combining effect. Maybe you guys learn in your circuit theory. Okay, both of these interchangeably, or okay, but this as long as you understand what is that. So from the appendix, AF1, okay, AF1 plus BF1, BF2. Okay, you can see this is your function 1 and this is your function 2. Okay, and you have A is actually the amplitude scaling, for example. Okay, for example here you have amplitude scaling. So if it's linear and superposition, you will have output the same thing as the input, which is, if this is A, this is A here in your frequency domain. Okay, linear means because it is similar changes. Okay. So first, okay, go to the example 2. You can see that this linearity is here. I put here. Okay, I put so that easy. Otherwise, I keep on referring to our table while I'm teaching. Okay, so you see here, find the Fourier transform for signal GT as shown. Okay, you are given this signal. Okay, and this signal is actually you cannot find directly from the table, but you know it is consists of several basic shape that actually introduced in the table. Okay, so you can see this one, your GT, okay, is actually combination of two rectangular wave. Okay, one that is the shorter one, and this one is the taller one. Okay, so you can see this is actually the rectangular function. So you can know that actually signal G can be produced by using superposition between two signals. So G is actually G1 plus G2. Okay. So example 2, we continue. Okay. you see that G1 rectangular T over 6, okay? Here, rectangular here, T over tau is equals to 3, okay? And then, sorry, tau over 2, okay? Tau over 2 is equals to 3, okay? Tau over 2 is equal to 3, that's why your tau is equals to 6. Okay, this one is tau over 2 equals to 1, and this means that tau equals to 2, okay? Okay, tau over 2 equals to 3, and then you get tau equals to 6. This is tau 1, okay? The other tau is actually equals to 2, okay? Okay. So from table C2, okay, you'll be using C1, C2, and so on, okay? But this one is this chapter, if I'm not mistaken, C1 and C2, So you have G2 is rectangular T over 2. Okay, then A rect T over tau. You know this actually the equivalent in the Fourier transform is actually AT sin omega tau over 2. Okay, there is a bit maybe a bit wrong in this. Okay, you guys need to be careful. Okay, in the way of writing, because sometimes it's wrong. Okay, wait. Can you guys respond in Google chat why I say this one is wrong? This one. Why I say this equation is wrong? Can you respond in Google chat? You guys know why is it wrong? Why the question is wrong? I mean, do you guys know why I say it's wrong? It's not entirely wrong, but something missing there. Something missing, that's why it is wrong. Do you guys know or not? Do you guys know or not why is it wrong? Okay. Not sure you guys know or not. This one should be like, for example, you need to write, for example, Fourier, right? You need to write Fourier of time domain. The function here should be here, okay? And then the function here, I mean the red, all of this will be only can be set as equal to. Otherwise, you cannot use equal to. You can use maybe arrow, for example, okay? Because this is never the similar, okay? Because this one is time domain, this is frequency domain. So this a bit error there, okay? Then you see here, okay? So you can see because of the superposition, it's just a plus in the signals, okay, of the in the frequency domain. So time delay, okay, sorry, time shifting. Time shifting. So time shifting, if you refer to the table, okay, first you refer to the table, you see the type of operation. So it's time shifting, and then you can see every shift of negative tau, negative t naught actually will be translated to negative omega naught t, omega t naught in the frequency domain. Okay, so there will be no change in magnitude logic because only change is time. So why there should be change in magnitude? So no change in magnitude, only change in the phase. Okay, for example here, if you have a range, okay, shifted by t naught, in frequency domain it will be negative j omega t naught. Okay. So here example, find the Fourier transform for signal 3e negative 2t minus 0.5. Okay. First of all, you need to find the common signal. Okay, the common signal actually shown in the table. Okay, it is 3e negative 2t, right? Okay, if you see from the table here, okay, it is actually this function, symmetrical decreasing exponential function with the t inside. Okay. Where were we? Okay, so EAT, okay, real numbers, and then you see, first you need to identify first, then you know this actually shifted by 0.5, okay, by 0.5 because of the signal. So first, actually you perform the standard function, okay, and the standard things that you actually found from the table, and then you actually introduce the shift. This one is negative t 0.5, and you just plus with for the frequency domain, you just e j omega over 2. Why omega over 2? Because it's actually times by half, because we have half of time shifting, okay? And the rest is accordingly, okay? And then you see there is a shift here, okay? There is shift in time domain by 0.5, okay? By 0.5 going to the right, okay? But in frequency domain, it will be like a phase shift, okay? Due to the time shift in time domain. So find the Fourier transform for pulse signal Vt, okay? Fourier transform. So you can see actually this signal is actually initially it should be rectangular, right? In the middle, okay? In the middle, okay? You can see it's actually shifting, right? It's actually shifting. So shifting all to the positive region. So this is one of the example of the pulse signal of the shifting of signal, or what happened. Okay. So okay, where was he? Where was I? Okay, so the signal Vt is regular signal which has been shifted by tau over 2. Okay, you know, right? The initial is that we have tau over 2 on the right and tau over 2 on the left of the negative, which is the negative region. So now it is shifted all to the positive region by tau over 2. So the Fourier transform for the signal is, okay, a tau, for the Fourier one is a tau sin omega t over 2, and with this e j omega tau over 2, because this is the shifting that has been applied to your time signal changes, then we change it to the frequency domain, okay? Next is actually time scaling. Okay, this one is also quite straightforward. Okay, time scaling, you have FAT. Okay, this is your scaling time in time domain. Then when we want to change to our frequency domain of the time scaling signal time domain, you're going to have 1 over modulus of A, F, and omega divided by A. Whatever omega function you divide by, omega here, you divide by A. So here is actually if A signal, okay, the signal will be compressed, but the signal will produce expansion in frequency domain, or else, okay, this one you can read on your own. Okay, I just want to show example first. Sorry. So if you have where's my pen? So if you have a less than 1, then you have a greater than 1. Okay. Okay. If a less than 1, what happened to your signal in time domain? Is it compressed or is it expand? Wait, I'm arranging my screen. Okay. So if the signal is actually a less than 1, okay, what is actually happened to the signal is that the signal will be expand. Okay, for example, this one. Okay, this one is just example, so that you can understand it better. Okay, and then what happened if the signal is actually greater than 1? You will have a more slimmer one. Okay, slimmer function. Okay, slimmer graph. So what happened to the omega domain? Oh, okay, sorry. I used the wrong one. Wait, I used the wrong example. Okay. So if a less than 1, so you have this one which is expand. And then if you have a greater than 1, you will have is compressed. Okay. Much shorter, but the same amplitude because it's only changes in time. Then what happened that when we have a less than 1, the signal will be expand. However, in the frequency domain, it will be compressed. Okay. And how about if you have a greater than 1, your signal in time domain will be compressed. However, in frequency domain, it will expand. Okay. So this is your time domain. This is your frequency domain. Okay, so you see, okay, this one is explain what I explained. Okay. Okay. The next is time inversion. Okay, time inversion, maybe you will learn in your tutorial as well. Okay. This one also direct, okay, which you have a negative time in time domain, which is the inversion. Okay, inversion. So it will translate to similar inverse in your frequency domain. Okay, you see here is f omega. Now you have negative omega. Okay, you can try this example at home. I cannot do this. Okay, this one is the one that actually that indirectly we did in the previous tutorial because there is duality involved in the previous tutorial. So actually duality, you can read this on your own. You can read this on your own, but I just want to make it easy. Okay, okay, duality is that where is pain? Okay, duality is that, for example, if you have signal in the time domain, okay, if you have signal in time domain, oh, okay, what happened? Okay, so if you have signal, this one is time domain, and then you have signal in frequency domain. Okay, then this one. So in the time domain, for example, you have a rectangular signal. Okay, then in frequency domain, you have sing, right? How is this? I like this. Okay. So the duality is that instead of having now you have the same shape of sing, but it is in time domain. Then you will have, when you want to obtain the time domain for this sync signal, okay, you will have a rectangular. Okay. However, when we want to convert, okay, when we want to convert things, not to convert, when we want to obtain the one that having this duality, okay, you need to times by 2 pi. You need to sum by 2 pi, and there will be a phase inversion, okay, phase inversion of negative pi, okay, a negative omega there, okay. So we'll have the same form as time signal, but having inverse operation of frequency, yes, and amplitude scaling of 2 pi, okay. So you see this A sin T, wait Oh, this one is already explained by me. I mean, it's already explained just now, okay, but wait okay. So the question is about, you see, the question now is GT A sin A tau sin T sin T over tau over 2. Okay. Okay. So you see this one is time domain signal. However, the signal is actually sync shape. Okay. So you need to do the duality to obtain the signal in the omega. Okay. So what you learn is actually A rectangular, right? A rectangular T over tau. Okay. For the time for Fourier transform, and then you will have A tau sin omega tau over 2. Correct me if I'm wrong, because I don't really look at the table, okay? Then you see when you want to convert, okay, you can see this is actually the given signal here, okay? The given signal here. Okay. And then you have, and then you need to convert. When you convert, you're going to have a signal that is actually in the okay, in rectangular. So you have 2 pi, okay, and then the signal G is actually in negative omega. Okay, this is your rectangular. So 2 pi A rect, okay, A rect, and then you will have G, not G, sorry, you have rectangular, and then you have omega over what? Over 2, over tau over 2, okay? Omega over T, I think, sorry, omega, when over T, okay? So when you sketch the graph, okay, then you have negative tau over 2, then you have tau over 2, okay, the domain, frequency domain, then you have 2 pi a as the amplitude. Okay, that is your what they call just now, time what just now? Sorry, duality. Sorry, forget the name. Duality. Okay. So it's also shown in your slide there. Okay, you can read. Okay, this one. Okay. Next is actually about the modulations. Okay. Okay, so frequency shifting modulation. So just like I told you guys just now, we do modulation. Okay, we do modulation actually to carry, for example, the information signal to larger distances. This is one of the application of modulation. Okay, so when we want to modulate, okay, when we want to modulate in exponent, okay, for example, in exponent representation, you have the signal is introduced with a e negative j omega naught t, okay, and results in frequency domain which is omega minus omega naught. Okay, this one I think you guys indirectly know already. And then this one is cos omega naught t. Okay, this is the carrier. Okay, this is the carrier signal, and this is the we call it modulating. Okay, modulating signal, and both of these will produce modulated signal. Okay, so this is modulating signal, this is carrier, and both of them will produce modulated signal. So you don't need to take to really know about this much. Okay, later on you will study in principle of communication, if I'm not mistaken, later after this subject, maybe next semester or next semester. Okay, so when you have cos omega naught, okay, you actually will have half version, half of them with v omega naught omega minus omega naught and v omega plus omega naught. So means you will have two signals. Okay, when you modulate, you will have two signals. One should at the lower region, which is omega minus omega naught, and the other one is omega plus omega naught. Okay, and you have two, and this sync you have 1 over 2j. Okay, you know why we have 2j here, right? Okay, is something from previous chapter. Okay, you guys should know already. Okay, so find the Fourier transform for signal gt ft cos 20t where ft to rect t. Okay, you see the signal here, the signal gt. Okay, we should have a continuous cosine signal. Why do you think we only have cosine signal and stop at -1 to 2 only in the time range? Why? Do you guys know why? Why we only have the signal in from -1 to 1 only? Why it's not continuous? Because cos is continuous. Okay, Chinto answer. How about the others? You guys need to able to to try to guess, to understand, because in exam maybe they give the signal and you need to find how to actually get the signal. Other than Chinto, how about the others? Only Chintong answer. I have 30 something in the class, but only Chintong is answering. Not sure where is the other. Maybe sleeping. Okay, so it's because of the rectangular function. Okay, rectangular function. So you have, that's why it's limited from -1 to 1, following the rectangular. And you see, is we have 2 times 2, so it's 2 maximum here. Okay, so you do the modulation, you will have half of the f Fourier of this, which is omega minus 20, and the other one is omega plus 20. Okay, because this is cos signal, so this is 1 over 2. Otherwise, it is 1 over 2j if it's a sine. Okay, so 2 sin over, and then you will do like this as you normally do, and then we actually obtain it is the half of the value, which is here. Okay, which is half times 2, you only have 1. Okay, so it's half of this amplitude, which is 1. Okay, and this one is actually delayed by 20, and this one advanced by 20. This one is minus 20, this one is plus 20. Okay, forget about this one. Okay, convolution. Okay, convolution. Okay, before we start, go to your e-learning. Okay, I already update something about group assignment, but there is no group task yet. And I forget, maybe Turkey need to tell me again, I need to check who actually dropped from my class, because there is 2 guys with the same name, almost the same name. I don't know which one. Later on I will check. Okay. So you see your group assignment. Okay, I added something here. Okay, group list here, and then there is lecture slide on convolution. Okay, like this. So it will show you actually the convolution, what it is involved for the time domain. Okay, which is actually integration. Okay, which is actually integration from negative infinity to infinity. Okay, it's a bit messy, but in frequency domain it will be easier, because in frequency domain it will be just multiplication. Later we cover. Okay, just I would like to show to you, this is the convolution. Okay, lecture slide on convolution. It is self-assessed. You can discuss with your friend, and then you will need to use MATLAB to perform convolution. I will give the group task, and then you have some time to actually read before actually you start the group task, because once I give the group task, you guys will have 1 month period to you already have to start 1 month, and I mean 1 month and submit. Okay, so use your time now just to understand. Okay, where were we? Okay, convolution. When we learn maybe digital electronics, maybe this one also, this, okay, where we have input, then we have output. So you have the system in the middle. Okay, LTI system. Do you guys know what is LTI? What is LTI? Do you guys know what is LTI? Do you guys know? Okay, so it's linear time invariant. Okay, you need to know. Sometimes they use short form, or What is linear time invariant? Okay, linear time invariant is actually linear time invariant is that actually what you have your fixed input. Okay, fixed input changes will provide the same fixed output changes, something like that. Okay, you won't have something different. For example, if you have something different, for example, if you insert t minus 1, and later on you in frequency domain, it will be like omega minus 1, minus 2, minus 3. Okay, initially it's t minus 1, and then in omega become, and then in omega something become omega minus 3. So it's not invariant because the similar changes in input doesn't provide similar changes in output. So this one means it is a time varying system. Okay, if it's the same changes in input translate to the same changes in output, it called as a time invariant system. Okay, it only impact fixed changes from fixed changes that we introduce in the time domain. Okay, so this is the LTI system. So you have from input to actually go to an LTI system, which we call it HT. Okay, this one is convolve. Okay, input signal XT convolve with your HT to produce output signal, which is your YT. Okay, so this is what you call as convolution, and this one they call it impulse response. They can call it transformer. Okay, but as long as you understand, I call it transformer. Okay, because it's transform the signal, but it's the same. Impulse response also the same. Transfer function also, sometimes they also call this one transfer function. Okay. Okay, you can see here for this table, it's actually F1 convolve. For example, this one XT convolve with HT. Okay, to produce YT. Now we want to see what is the Y omega. Okay, so actually in time domain, in order for us to do the convolution XT or convolve with HT, this is the integration. Okay, so if it's in frequency, it will be much simpler because it is just a multiplication. Okay, for example, V1 convolve with V2T is actually convolution of V1 omega. I mean, it's actually just multiplication of V1 omega with V2 omega. Okay, so example 7. Okay, given two signal, you can see there is two signals here, negative A T UT and negative BT UT. Okay, so what does it mean by this? It means that we only have signal at the value of greater than 0, because this is a unit step, and then it's given A 0, B equals greater than 0. Okay, so the relevant graph is actually the decreasing exponential function. Okay, so here, so F equals to F1T convolve with F2T. Okay, then when we want to see in the frequency domain counterpart, it is actually F omega equals to F1 omega times F2 omega. So we have 1 over A j omega plus A B j omega. Okay, the rest below is actually just mathematics. Okay, but this is the concept, okay, that you need to understand. So because if the question gives you something else, you should know that whatever convolve in time domain will result in multiplication in the frequency domain signal. Okay. Okay, this one is same. Okay, differentiation. Differentiation is actually when we differentiate the signal. Okay, we differentiate D and DT. We have order of differentiation. We can have first order, second order, and the rest. Okay, so if you see this equation, okay, from the table, you have dn over dtn. So if it's first order, it will become d over dt. Okay, if it's a second order, it will be d square over dt square. Okay, something like that, and so on. Okay, when we I use this one, is much more clear. Okay, and when we do the differentiation of the time domain, okay, and we want to find this counterpart, frequency counterpart, it's just actually j omega n v omega. Okay, dn here. Okay, if it's second order, d square vt over dt square, it will become j omega square. Okay. So these signals is actually, they give the triangle. Okay, you can see Okay, we have these signals. Okay, wait. Okay. Okay. So actually, how we actually obtain this one? Okay, and how we actually obtain this one? Do you guys know it? This one is just like ymx plus c. Okay. For example, at plus a. Okay. This is the first part, which is the positive, and then you have the negative part at plus a. Okay, negative because this one is gradient negative. This one is gradient positive. Okay, so it's actually a plus. Okay, but to make it short, this is a triangular T. Okay, and then when we want to do the differentiation, when we want to differentiate still in time domain, okay, you differentiate, you will have differentiate this one. You only have this one differentiate. You will have the only constant, which is a. And the next, when you want to differentiate this one, you have negative a here. Okay. And then if we want to differentiate further, you will have an impulse. Okay, you will have an impulse. Then the rest, you see dgt. Okay, dgt, then actually differentiate of your signal a tri t. Okay, you will have a rectangular t 0.5 and a minus a rectangular t 0.5, 0.5, this one. Okay, and then when we do the second order differentiation, we will actually obtain the answer in impulse form. Okay, as both you can do which one, or maybe question will ask you to do what. For example, if they want to ask us to do first order differentiation or second order, or depends on you. Also, there is advantage in this. I mean, there is things to do around with it. Okay, so if it's first order differentiation. Okay, you have the rectangular, right? Rectangular, and then this is the result of your dgdt. So you put j omega, g omega. Why there is no power, only power of 1? Because this is first order. Then you know actually, right, the Fourier transform of a rect t is actually sinc signal with j omega over 2. Why omega over 2? Because this half is actually coming from here. And minus a rectangular, a sinc omega over 2 and ej omega over 2, which is this. Okay. So then you know, then you do some arrangement. You see a sinc omega over 2 is actually ej omega over 2, and that's like this. Okay. Then you do the ordering. Okay, you do the ordering. You will obtain at the end is actually a sinc omega 2 or a sinc square omega over 2. Okay, in the frequency domain. Now we try to do the second one, is the second order differentiation. Okay, second order differentiation. You can see actually the differentiation of dgt over dt. Okay, you put like this, right? Okay, there is something. I think I show you guys or not just now. I forget. My mind is not sure if I. Okay, never mind. Just ignore. Okay. Okay, second order. So J is actually negatives. Wait. Okay, when we do the second order differentiation, this one will be J omega. Okay, J omega square. Then you only have, then you will have square here. Then you know that J is actually what? J is equal to what actually? J is equal to what that we actually have negative here? Do you guys know what is J? Do you guys know what is J? Yes, from your secretary, okay? It is negative 1. So that's why J square is actually, what I'm doing, is actually square root of negative 1 square, okay? And you guys know, right, everything that we square, it will have positive number. And 1 will always be 1. So 1. So it's J, okay? Here. And then omega square, then you have this function, 2 cos minus 1 and so on, okay? Then you will have your signals, okay? You have your signal, which is a sin square over omega over 2, okay? You can see a sin square omega over 2 for the second order differentiation. And you can see this one is also a sin omega 2, okay? A sin square omega 2, okay? You see this one is a sin square omega over 2. For the second order, the first order is also a sin square omega over 2. Okay. Oh, we finished very fast. Huh? Okay. Do your tutorial. Okay. Do your tutorial. Okay. Very fast. I should start from chapter 3, part 3 later on. Okay. Go to your tutorial. Okay. And then do question number 2 and 3. And just as usual. Okay. Just as usual. You actually will add your... Abdul Rahman, how come you add so early? The class not even start. What you put here? Oh, okay, funny. Because I'm just we just finished the lecture. Okay. So okay, mid class. Okay. For example, Chintong. Okay. I learn about signal convolution. Okay, in time domain is the multiplication of signal in frequency domain. Okay, and pause. Okay, maybe Abdul Rahman want to leave my class very early. Okay, so we actually finish. We actually finish chapter 2 part 3. Okay, I give you some time actually before the group task. Okay, it's good that you don't receive group task first. You learn by yourself and your group member. I will give the latest group member today. So that the leader and the group can manage themselves, create WhatsApp group to discuss. Okay, so this is your convolution lecture. Okay, and then the test, don't forget, the quiz, don't forget, it is all chapter 2, and then 1 is about definition, but not straight, means it will test your understanding just like the previous quiz 1. And then you have 3 questions which is easy, and then you have you have the question which is difficult. So divide your time. Okay, you will know the question difficult when you see it. Okay, and you know which question is a bit easier when you see it, because you know, oh, easy, you can do it. So don't spend so much time on the easy one, because you have only 30 minutes and 2 minutes submission time. 2 minutes submission time is actually not 2 minutes for you answer. 2 minutes try to submit, because you don't know internet. Okay, and because the quiz is given 24 hours, okay, period. So you need to know which time is okay. You need to find the best position, whatever, for you to state the quiz. So the quiz 30 minutes, submission time 2 minutes, and the question cannot be resubmit and cannot be reattempt. Okay, and you cannot know your mark. Okay, you cannot know your mark. So this is totally different from the quiz one. Okay, you guys can put there. Okay, okay. If you guys already put, you can just leave the class. You guys can start do the tutorial, because tomorrow you'll be in class exercise for the tutorial. Okay, so use this time to do your tutorial. Also fine. Okay. because you have another 1 hour, right? I dismissed the class early because we finished the lecture early, okay? I'm not sure whether maybe I'm too fast. I'm not sure. Because the other section, I spent around 1 hour 30 minutes. The other section, I don't know why you guys only 1 hour. I hope you guys understand, because sometimes maybe I overspeed and maybe sometimes I speed, but at least you understand, okay? So you may leave the class. You may leave the class when you already post what you have learned for today, okay? Thank you.
Okay, thank you, Doctor.
Welcome.